Today, I'm very glad to present our paper. I'm Xinguang Chen from the Chinese University of Hong Kong. First is the problem definition. Empirical entropy is a classic concept in data mining and the foundation of many other important concepts like mutual information. To begin with, we'll give the definition of empirical entropy. Given the input data set D and an attribute alpha with support size mu alpha, the empirical entropy Hd alpha of attribute alpha is defined as the following formula. In this formula, Ni is the number of occurrence of attribute value I in the dataset, and N is the number of records. Take this small table as an example. There are 3 records, R1, R2, R3. Each record contains 2 attribute values of alpha1 and alpha2. For alpha1, all values are the same, so Hd alpha1 is 0. For alpha2, N0 is 2, N1 is 1, and N is 3. So Hd alpha2 can be calculated as follows. Next is the definition of empirical mutual information. Given the input dataset D and 2 attributes alpha1, alpha2, the empirical mutual information ID alpha1, alpha2 between alpha1 and alpha2 is defined as the following formula. Following the above example, we want to calculate the empirical mutual information between alpha1 and alpha2. Since we already have Hd alpha1 and Hd alpha2, we only need to calculate Hd alpha1, alpha2. Using Hd alpha1, Hd alpha2, and Hd alpha1, alpha2, we can get ID alpha1, alpha2. In the literature, empirical entropy or mutual information is widely used in feature selection, hypothesis analysis, decision tree learning, graphical model structure learning, and categorical clustering. In this paper, we focus on 2 types of queries, the top K and filtering queries on empirical entropy and mutual information. For top K query, given the input dataset D and a positive integer K, it aims to return the K attributes with the highest empirical entropy or mutual information scores. For filtering query, given the input dataset D and a threshold eta, it aims to return all attributes whose empirical entropy or mutual information score is no smaller than eta. A straightforward method is to derive the exact score by scanning all records, which is too expensive on large datasets. Luckily, in most real applications, such as feature selection, error-bounded approximations of the empirical entropy and mutual information are usually sufficient. To answer queries efficiently, we first define approximate top K query as follows. Given the input dataset D, a positive integer K, an error parameter epsilon, and a failure probability Pf, as alpha is the exact score, either the empirical entropy or mutual information of attribute alpha. S hat alpha is the estimated score of S alpha. Alpha 1 star, alpha 2 star, and alpha K star are the K attributes with the top K score such that the following inequalities are satisfied. Then it returns K attributes alpha 1 prime, alpha 2 prime, and alpha K prime such that the following holds. Condition 1 requires that the estimated score of the returned K attributes are accurate enough. Condition 2 requires that the returned I's attribute has a score close to the exact I's largest score. Combining conditions 1 and 2 assures that the returned approximate top K answers are close to the exact top K answers with theoretical guarantees. Take a table with 4 attributes and 6 records as an example. H alpha is the exact empirical entropy of attribute alpha. H hat alpha is the estimated score of H alpha. We want to answer the approximate top 2 query on empirical entropy and epsilon is 0.5. When sampling R6, R1, R3, R5, we have the estimation of each empirical entropy score as follows. Besides, suppose that we have their exact values. The attributes with estimated top two scores are alpha 3 and alpha 1. So alpha 1 prime is 3, alpha 2 prime is alpha 1. Since h hat alpha 3 is larger than h hat alpha 1 and so on. Alpha 1 star is alpha 3. Alpha 2 star is alpha 1 since h alpha 3 is larger than h alpha 1 and so on. We then return this to alpha 3 and alpha 1 for the approximate top two query because for I is 1, that is alpha 3, its estimated empirical entropy score is close to its exact score. Also, its exact empirical entropy score is close to the real top one empirical entropy score. For I is 2, we can verify that it satisfies these two conditions in a similar way. Then we define approximate filtering query. Given the input dataset D, a threshold eta, an error parameter epsilon, and a failure probability PF. As alpha is the exact score, either the empirical entropy or mutual information of attribute alpha. Then we return a set X such that if S alpha is larger than or equal to 1 plus epsilon times eta, alpha must belong to X. Else, if S alpha belongs to an interval, alpha may or may not belong to X. Otherwise, alpha should not belong to X. Take the same table of the previous slides as example. Recall that H alpha is the exact empirical entropy of attribute alpha. H hat alpha is the estimated score of H alpha. We want to answer the approximate filtering query on empirical entropy when eta is 1 and epsilon is 0.1. When sampling R2, R4, R3, R6, we have the estimation of each empirical entropy score as follows. Besides, suppose that we have their exact values. The estimated attributes with empirical entropy scores no smaller than eta are alpha 1, alpha 2, alpha 3. Return a set as alpha 1 including alpha 1, alpha 2, alpha 3 for approximate filtering query, because we can verify that for all attributes alpha, the conditions of approximate filtering query can be satisfied. For alpha is alpha 1 or alpha 3, H alpha is larger than or equal to 1.1. Alpha must belong to X. Indeed, alpha belongs to X. For alpha 2, H alpha 2 is larger than 0.9 and H alpha 2 is smaller than 1.1. So alpha 2 may or may not belong to X. Indeed, alpha 2 belongs to X. For alpha 4, H alpha 4 is smaller than 0.9. So alpha 4 should not belong to X. Indeed, alpha 4 is not in X. The state-of-the-art sampling-based solution is proposed by Wang et al. Their main idea is to sample a subset S of the records from the input dataset D and then derive an estimation of the empirical entropy or mutual information. They solve some challenging problems. The first one is the biased estimation of empirical entropy. So they derive a bound between the exact value and the expectation of the estimation. The second is that classic concentration bounds like Chernoff bound or macrodynamics inequality cannot be applied to bound the gap between the estimation and the exact empirical entropy. So they use concentration bound by sampling without replacement. For top K query, their entropy rank return run in batches and adaptively sample records. It derives lower and upper bound of empirical entropy or mutual information score for each attribute, and distinguish the lower bound of the attribute with the k's largest score and the upper bound of the attribute with the k+1's largest score. For filtering query, the entropy filter run in batches until the upper bound of the empirical entropy or mutual information is smaller than eta, or the lower bound is larger than eta. Their main deficiency is that it returns the exact answers for the top K and filtering query. It's expensive when the K's and k+1's largest score are close on top K query, or the score and eta are close on filtering query. Next is our contribution. The first is approximate top K query processing. We have improved time complexity on empirical entropy or mutual information. We achieve 2 orders of magnitude improvement over alternatives in our experiments. For approximate filtering query processing, we have improved time complexity on empirical entropy and mutual information. We achieve up to 77 times faster than alternatives in our experiments. For approximate top K query processing, the main idea is to increase the sample size adaptively. We derive tighter and tighter bound and check if the conditions are met to return the answers satisfying the definition of approximate top K query. We design a stopping condition as follows. S underline alpha or S overline alpha is the lower or upper bound of the score, either the empirical entropy or mutual information of attribute alpha. We stop the iteration once for all returned attributes. The lower and upper bounds of the score satisfy the relations as the inequality shows. This will make sure that the result satisfies the definition of approximate top K query. We also derive the running time of our algorithm, which is linear to 1 over the square of the exact K's largest score. Besides, to reuse the records of the previous iteration, we show that for W0, W1, for sampled records without replacement, W0, W1, Wn forms a martingale process. With this result, the concentration bound can still be applied even though there exist dependencies among the samples in different iterations. For approximate filtering query processing, our main idea is to adaptively increase the sample size step by step until the stopping condition is satisfied. We designed a stopping condition as follows. Recall that S underline alpha or S overline alpha is the lower or upper bound of the score, either the empirical entropy or mutual information of attribute alpha. The stopping condition includes 3 cases. In case 1, if the lower and upper bounds are close enough, justify attribute alpha based on its current estimation. In case 2, when the lower bound is large enough, include alpha in the result set. In case 3, when the upper bound is small enough, ignore alpha. The expected running time of the algorithm is to answer the approximate filtering query is as follows. It's linear to 1 over the square of eta. Now we introduce our experiments. For experimental settings, we use 4 large real datasets. They are publicly available. For empirical entropy queries, we compare our swap top K query algorithm or filtering query algorithm against the state-of-the-art top K query algorithm or filtering query algorithm in one's paper, termed as entropy rank or entropy filter. We further include the exact solution, termed as exact, as a baseline. For the empirical mutual information, we also include entropy rank, an entropy filter, and the exact solution as our competitor. For parameter settings, all our algorithms include a failure probability parameters, PF, where set PF is 1 over n for our swap, entropy rank, and entropy filter, where n is the number of records. For top K query, where vary K in 1 to 10 and show the results for K equal to 1, 2, 4, 8, 10. For filtering queries, we vary eta in empirical entropy filtering queries as follows. And we vary eta with 0.1, 0.2, 0.3, 0.4, 0.5 in empirical mutual information filtering queries. We use different settings of eta since the empirical mutual information scores are typically smaller than the empirical entropy scores. Our swap includes an error parameter epsilon to control the trade-off between the query accuracy and query efficiency. We tune the impact of epsilon in the experiments. The experiments show that when epsilon is 0.1 or epsilon is 0.05, it achieves the best trade-off between the query efficiency and accuracy on empirical entropy top K queries or filtering query. When epsilon is 0.5, it achieves the best trade-off between the query efficiency and accuracy on both the empirical mutual information top K and filtering queries. In the experiments, we set this value of epsilon as default values in our corresponding top K and filtering queries. Here is the experimental results of approximate top K query on empirical entropy. In the first figure, x-axis represents various k and the y-axis here represents the running time of 3 methods: exact method, entropy rank, and our solution on each dataset. In the second figure, y-axis indicates the precision of the answers to the query. As we can observe, our swap is consistently outperforms entropy rank and is an order of magnitude faster than entropy rank in most cases. Compared to exact, our solution further achieves up to 3 orders of magnitude improvement in terms of accuracy. All 3 solutions provide the exact top K answers, achieving 100% accuracy in all cases. Here is the experimental results of approximate filtering query on empirical entropy. In the first figure, x-axis represents various eta and the y-axis represents the running time of 3 methods: exact method, entropy filter, and our solution on each dataset. In the second figure, y-axis indicates the accuracy of the answer to the query. Again, our swap is up to an order or 3 orders of magnitude faster than entropy filter or exact in most cases. In the meantime, our algorithm correctly reports all the attributes with empirical entropy no smaller than threshold eta in all cases. For approximate top K query on empirical mutual information, swap is still the most efficient algorithm among all methods. It's up to an order or 2 orders of magnitude faster than entropy rank or exact. In terms of accuracy, all the methods still provide identically highly accurate results. For approximate filtering query on empirical mutual information, swap is up to 54 faster than entropy filter and 2 orders of magnitude faster than exact. In the meantime, swap reports identically accurate results as entropy filter and exact. This is the end of our presentation. Thanks.